Hello, welcome to this series of tutorials on solution of partial differential equations. But now we are going to look at a system of partial differential equations. That is, we will have more than one partial differential equation which we need to solve for. We will start by implementing the code for shallow water equations. So these are basically a set of three equations which will result in solutions which will look very interesting, like the one which has been displayed here. This is basically the Wikipedia page, so you can come up here and look at these equations. So these are three equations. The first one is for mass balance, the second one is for momentum in x direction, that is conservation of momentum in x direction. This one is for conservation of momentum in the y direction. So these three set of equations, if solved simultaneously, will result in solution which will look something like this. So we will attempt to code this particular system of equations to start with. Initially we will start with a very simple code wherein I'll not look at a generalized framework, but I'll be specific to this particular system of equations. And then later on I will be doing a set of videos wherein I will be looking at the system of equations in a more general perspective. Well, here you have this eta, which is the height of the water column, u, which is the velocity in x direction, v, which is the velocity in y direction, and we also have this g, which is a constant, which is the acceleration due to gravity. So these equations together will result in a solution which will look something like this depending on the initial conditions that we imply. Okay, so let's look at these equations in a more general framework. The current code, that is the two-dimensional Cartesian code, is capable of solving a single equation which looks something like this. So del u by del t plus del f by del x plus del g by del y equal to 0. So this is the equation which we are already capable of solving in our code. So this is a scalar equation because u is a scalar. And now we are interested in solving a system of partial differential equations. So from here, how do we go to a system? So we are interested in going to a system of partial differential equations. So let's write the three equation system like the one which we have seen for the shallow water equation. So let us call the three variables as u1, u2 and u3, that is the conservative vector. So we will have the first equation as del u1 by del t plus del f1 by del x plus del g1 by del y. This is g is equal to 0. Then the second equation we can write it as del u2 by del t plus del f2 by del x plus del g2 by del y equal to 0. This is our second equation, and similarly we have our third equation which we can write it as del f3 by del x plus del g3 by del y equal to 0. Now if you try to compare this system of equation with the equations that we have, so here eta u and eta v are u1, u2 and u3. Eta into u is f1. This whole expression in the brackets is f2. This is f3. This is g1. This is g2, and this expression in the bracket is g3. So we have this system. Now we have written it in a slightly generalized form. So it's normally useful to write it in a slightly more compact form because these three equations are kind of are written over 3 lines. Instead you can write it in a slightly more compact form by writing it something like this. So notice here that u is a capital letter here instead of the small case that we have used earlier. So u is a capital letter, and F is a capital letter again, and G is a capital letter as well. So what are these? U, F and G. We can write just to have the same expression. U is going to be equal to U1, U2 and U3. F is going to be equal to F1, F2, F3, and G is going to be equal to G1, G2, G3. And we have no source terms here. Well, in the shallow water equations, if you also consider the friction at the base of the water, and if you consider the viscous fluxes and so on, then you will also have the right hand side. In this case, the source terms are equal to 0. So you can see now we can write this system in a much more compact form. So this is the equation that we are going to deal with. So now we have U, F and G, which are vectors and no more scalars. Okay, now I'm going to introduce a little bit of complex stuff. It may not be complicated if you already know about it, but if it's the first time that you're looking at this system of equation, then you might find it a little bit complicated. And I'm not going to go into the details as of now, but in the upcoming videos I'll go into it in much more detail through a series of videos. But as of now, let's say that okay, we can calculate the so-called derivatives of the vectors, so del F by del U, which is called the Jacobian. Okay, before even doing this, let me just say why do we need to calculate these derivatives here. So let us consider this scalar case. Now in this scalar case, let us look at this particular term, del F by del X. Now you can write this term as using the chain rule as del F by del U times del U by del X, right? And you see here, if you compare this particular term here, the one which is in bracket, this looks like the advection velocity, right? Because we used our advection velocity for calculation of flux through the cell interfaces. So this is basically AX, and similarly del G by del U is equal to AY, the one which we had used in our advection equation. So to calculate the velocities, we need to calculate these derivatives, and in case of vectors, they become the Jacobian. I'll be talking about this in much more detail later on, but this particular Jacobian is required for calculation of the velocities or at which the waves move. Also, the Jacobian also has the information about these waves, and I'll be talking about that in much more detail later as well. So okay, so I'll not go into the details as of now, but let's see what this Jacobian is going to be. This Jacobian is going to be basically a matrix, because now we are dealing with vectors. So when we take the derivatives of each of f with respect to u, we will have a matrix. So this matrix is going to look like, okay, let me first of all also say del f by del u is equal to, we will use a just for a shorthand kind of a way for del f by del u. So this will look like del, okay, del f1 by del u1, del f1 by del u2, del f1 by del u3, del f2 by del u1, del f2 by del u2, del f2 by del u3, and the last row is going to be del f3 by del u1, del f3 by del u2 and del f3 by del u3. So this is the Jacobian for this particular system. Okay, and one more thing that you must have noticed, I believe, I just forgot to mention it, that if you look at the terms like f1, f2 and f3, so you might have noticed that f1 is a function of u1, u2 and u3, or in principle they can be function of all of them. So this is a very important fact, because of this we cannot use our scalar code. Had we not had this dependency of f on u2 and u3, similarly g of dependency of g on u2 and u3, we could have solved these equations as if they are three separate scalar equations. So these are kind of coupled equations. Again, if I move to the shallow water equations, you will see that this f also includes u, g includes v, which are the other terms, that is the other terms in the conservative vector, and therefore we cannot solve this equation in isolation. These three equations are dependent on each other. As soon as something changes in height, also something might change in u and v because of the fluxes. So that's an important observation that I think you must have made. So now going ahead, we have the Jacobian and the velocities. Obviously this matrix cannot be the velocity of the wave. The velocity of the waves is given by the eigenvalues. So let's look at the eigenvalues and eigenvectors. So if I have the matrix as A, then we need to calculate the eigenvalues and eigenvectors of A. So okay, now it might be a little bit confusing at this point as to why do we need the eigenvalues and eigenvectors, but I'll do a series of videos just to explain what these all mean and where do they come from. So as of now, just take it as if we need some of the information. Actually we need the eigenvalues to write the Lax-Friedrich flux, and therefore I am going through this process, but it's just required for that particular one thing. That's why I'm going through the process. It's in no way a complete information regarding the theory of the hyperbolic partial differential equation. So how do we write the eigenvalues and eigenvectors? So we have A, let us say the right eigenvector is equal to lambda times r, and here this lambda is the eigenvalue, and this r, and if I can go there, okay, and these two are the eigenvectors. You will have three eigenvalues, and for each of the eigenvalue you will have a eigenvector. So it is important that we have distinct eigenvectors, and in that case the system of equation is called strictly hyperbolic. In this case, for the shallow water equation, we have three real eigenvalues, which are like for example, for del f by del u, the eigenvalues are going to be u plus or minus c and u, where these are the two eigenvalues and here we have one, so we have three eigenvalues associated with it. Now similarly, if you look at the another flux vector g, you can also do the same, and for del g by del u, the eigenvalues are going to be not u but v plus or minus c, and V. These are the eigenvalues for G. These are for F. Okay, what is C? I did not mention what is C. So C is equal to square root of G times H. So if you calculate the eigenvalues and eigenvectors for this particular matrix, then you will see, I mean for the shallow order equations, okay, this is particular to shallow order equations only. If you solve some different system, then you will have different set of eigenvalues and eigenvectors. At this point of time we are not interested in eigenvectors, and that is why I am not writing it down here. So these are for shallow water equations. These particular vectors are, these particular eigenvalues are also mentioned in this particular article on Wikipedia, where u plus or minus c are the characteristic speeds. Okay, now I have introduced one term called characteristics, so I'll also talk about characteristics and what do they mean. Basically, characteristics are the lines along which the solution does not change in the xt plane. So these are the eigenvalues. Okay, maybe I have introduced a lot of terms and I have not explained a lot about what I mean, but I'll be doing it in a later video. Okay, next let us look at the Lax-Friedrich solver, because that is the reason why we have come through all this. So we know that the eigenvalues are these for F and G. So okay, so for the Lax-Friedrich solver, the only eigenvalue that we need is the maximum eigenvalue. In other words, we want to see how much is the maximum extent of propagation of information from the cell interface. So that is what we are interested in. So in case of Lax-Friedrich solver, but in case of more advanced solvers which are much more accurate, we will need much more than that. We will also require the eigenvectors, and well, I'll be covering that later. Maybe I'm saying this so many times that I'm covering later, but yeah, just stay with me. So I have this lambdas. Now the if we take the absolute value and the max of all the absolute values of lambda, then this is the only eigenvalue that we need. So for the flux F, this eigenvalue, this maximum eigenvalue is going to be equal to absolute value of u plus c, and for G, it's going to be equal to absolute value of V plus C. So you can see this by looking at these three eigenvalues and these three eigenvalues. So the max of them is going to be absolute value of u plus c, and maximum value is also going to be, for the G vector, it's going to be absolute value of V plus c. Okay, and the Lax-Friedrich solver is, now we can write it as I'll write Riemann solver. I'm introducing one more term here. I don't know whether I have talked about Riemann solvers earlier, but again I'll be covering this later, so I'll be talking about Riemann solvers a lot in this series of videos. So in case of the Lax-Friedrich Riemann solver, it's very simple. The flux F, which is going to be you might remember from the finite volume video that for a rectangular cell, for the horizontal faces, the value of nx is equal to 1 and ny is equal to 0, and therefore only f is important for vertical faces, and for the horizontal faces nx is equal to 0 and ny is equal to 1. Therefore only g is important for the horizontal faces, and the flux at the interface for the vertical faces is going to be given as, using the Lax-Friedrich solver, which is a central Riemann solver. So it will be given as f left plus f right divided by 2. So left basically means this inside, right means outside. So this is left side, this is right side. Similarly, this is left side, this is the right side. Okay, so FL plus FR divided by 2 minus this value, which in this case is going to be absolute value of U plus C divided by 2 times UR minus UL. And so this is for the vertical faces. And for the horizontal faces, we are interested in G. So it's going to be equal to GL plus GR. So it's going to be equal to GL plus GR divided by 2 minus absolute value of G plus C divided by 2 times UR minus UL. Okay, and this is going to be for the horizontal faces. Okay, so we have the minimum required stuff for writing our code. So this is the only result that we are interested in as of now for calculation of the flux. So I had to go through this full process just to have this particular equations. I did not want to directly produce these equations and say that these come from somewhere, so I just thought I'll give a very brief introduction to what and how do these values come from. So the next thing what I would like to do is let us look at the code now. So we had this code which we had written earlier. Now there are some changes that I have made. Well, not much, but a couple of changes. The first change that I have made is, well, I have committed this particular project into Git. So that's one thing, and since we are attempting to do something new, it's a good time to put the project or commit the project to Git. Okay, and what else? Yeah, there is one mistake which I had done. Well, it does not affect the solution, but it affects the order of accuracy analysis. So the mistake was that I was dividing the error by number of X cells and not the total number of cells. So now I'm calculating number of cells, which is number of X cells times the number of Y cells in a two-dimensional domain, and then I'm dividing that the error by that particular total number of cells, and this is required only for the order of accuracy, and it will not affect the solution as such. Then there are a couple of more changes. I have introduced this method here which reads all the fields from the config file and makes a list of it and returns that particular string as a combination of all the variables which are existing in the config file and their values. This is done by using something called Java reflection, so that every time we add a variable, automatically the string will be created. And why is this important is I am basically printing out all the information from the config file to the console, so that it is much more easier to realize what the solution corresponds to, that is what parameters were used for getting the solution. So if I now run the code, you must have seen right at the beginning it prints out these values, that is all the configuration values. That is because I'm printing out here. Again at the end I am again printing out the values and the variable names from the config file. So this is the thing. It will help in understanding what the solution corresponds to in a much faster way, instead of having to go through the config file and looking it up. Well, that is fine, but sometimes the code you could have transferred the compiled code to a different computer, and then after you run the solution, maybe it might take say 2 hours, 3 hours to run, and after that once you have the solution, you might not have an idea as to what configuration was it using, because it's a compiled code now. So it's a good idea to have these configuration parameters printed out at the end of your simulation. Well, that's just one practice which I follow. You may or may not follow it. And using Java reflection, it becomes really very easy. I just can read out all the fields from that particular config file and just print it out. Okay, I'll pause this video as of now. I have some work to go to, so I'll pause this video and I'll continue with this video. Well, for you it's going to be instantly, but I'll be doing it after some time. So see you in some time. Bye bye.